Hey, welcome everyone. Today we have a fantastic talk by Jovan Stojkovic from University of Illinois Urbana-Champaign. Jovan did a lot of really interesting and multifaceted work published at ISCA and other conferences, pushing serverless systems in quite a few dimensions. So we are all very curious to see what about his latest work and also what's coming next. So welcome, Jovan. It's great to see you here. And also, I think this vHire community meeting is also one of the biggest ones in this history of our meetups. So it's great to have you here. Please take the floor.
Thank you very much. Thank you for inviting me. And I'm really happy to be here and to talk about my research today with all of you. So, hello everyone, I am Jovan. I am a fifth-year PhD student at University of Illinois. And today I'll present to you the work that I did during my PhD, which is chasing the tail at scale, designing server architecture in the age of serverless computing. So today I will focus on two emerging classes of software in the cloud. And as this community is very familiar with it, I will just give a very brief background. I will focus on microservices and serverless computing. Microservices are a way how we develop our applications. In the past, we had large monolithic applications, and now we're going towards decomposing them into many small interdependent services. Each service implements its own separate functionality, and then the end-to-end application are composed by having services communicating with each other over some interfaces such as RPCs. In this way, we can have scalability, meaning that every single service can be scaled up and down independent of each other. We have design simplicity, which means that different teams can develop different services. And also hardware management becomes easier because we can now decide on which hardware we want to run each of these services, and that could be potentially different and independent of each other. So in this way, we can make much large applications being used by with very simple programming interfaces. To take a step even further, we have serverless computing. With serverless computing, users will only deploy applications while providers will provision all the resources. With microservices, users would still need to deploy all the VMs, servers, decide how to create their resources, decide when to scale up and down, and have very complicated policies. In serverless computing, providers will do that on behalf of the users. In this way, we still maintain simple and modular programming, same as for microservices, but now we have automatic resource scaling. Again, this means that resources can be scaled up and down by the providers without having involved the users themselves. And also we have pay-as-you-go model, which means that users can pay only for those resources that they actually use. In this way, we can democratize the use of very expensive compute systems to many users. For these reasons, major cloud companies such as AWS Lambda, Microsoft Azure, Google, and IBM Cloud, they all have serverless offerings. In my PhD, I work towards designing cloud-native process architectures from the stack going from hardware up to the platform level. In this talk, I will focus on recent works that I did on the hardware side, which is 𝜇Manycore published at last year ISCA, and Mosaic that will be published at this year Micro. And I will briefly go over the EcoFaaS, which was published this year ISCA. So first, let's understand what is the main target, what is the main performance metric that we want to optimize for. In cloud environments, we want to focus on tail latency. In such applications such as microservices and serverless computing, the response time will be determined by the slowest service. Here we have front-end server, mid-tier server, and multiple backend servers. If one of these backend servers is slow, the whole application will suffer. Therefore, we do not need to focus only on optimizing for the average performance, but even more importantly, we need to optimize the performance at tail. So how can we design processors to be optimized for tail latency? We need to identify and optimize away those sources of contention, because contention is the major contributor to tail latency. In my work, I focused mostly on the contention sides of request scheduling and context switching. There are hotspots in request scheduling. As service requests come in bursts, meaning that we have many requests coming together, they need to be queued before execution. Therefore, how we design the queuing system can significantly impact the tail latency. In this figure here, we show the normalized tail latency and average latency as we change the number of queues in a 1,000-core manycore. For example, on the leftmost side, you can see 1,000 core queues per machine, which means that every core has its own queue. And on the rightmost side, you see one queue per machine, which means that all 1,000 cores share this same queue. In both cases, when we have many queues and when we have a single queue, we have very high tail latency. This means that when we have many queues, we have load imbalance. This means that some cores will have lots of work to do, while other cores will suffer from the lack of work. On the other side, if we have a single queue in the system, all of our cores, all of 1,000 cores, will compete for the same queue, creating contention. Tail latency in both cases suffers. However, even if we go for the optimal software queue, which has about 64 to 32 queues, meaning that 32 or 64 cores share the same queue, even then, the optimal software organization will increase the tail over average by more than 10 times. This suggests that we need a specialized hardware to support request queuing and scheduling in such environments where we have bursts of requests, and every request is a very short service with only about tens to hundreds of microseconds. On the other hand, we also have hotspots in context switching. As services spend majority of their execution time being blocked and waiting on I/O for two main reasons. First, they have remote storage accesses. As the service invocation starts, it will go and fetch data from the storage or write data to the storage, or it will call synchronously other services. During storage accesses or synchronous calls to other services, the service will be idle, so it will wait. This means that if we want to efficiently use our cores, we need to frequently context switch, and these context switches will be often across different services. In this figure here, every different color represents different invocations. So we can have gray thread executing, then being blocked, and then we continue with the purple thread. Then we move on back to the gray thread and so on and so forth. So we frequently context switch across different threads on our cores in the machine. However, as we have large overheads of context switching, the tail latency again suffers. In this figure here, on the y-axis, I show the normalized tail latency, and on x-axis, we have different context switch overheads starting from not reasonable 16 cycles up to 8,000 cycles. We have three different lines for 5, 10, and 50,000 requests per second. All of these experiments were done with DeadStar Bench microservices when simulating a min-SST framework. With Linux-based systems, the context switch overhead will be about 4 to 8,000 cycles. And we can see here that the tail latency compared to the ideal case, when we have almost zero context switch overhead, will be even about 40 times larger than the ideal case. However, even if we go to the optimal software solutions, these recent proposals such as Shinjuku, Shenango, and ZigOS, they reduce the context switch overhead, but it is still in the order of about thousands of cycles. We can see that with high requests per seconds, 50K RPS, we can still have more than 10 times increased tail latency just due to these context switch overheads. Again, these results suggest that we want to go towards hardware solution. In order to minimize the overheads of context switching, we would need a specialized hardware support. In this talk here, I will cover 3 works that will rethink the design of serverless systems for performance, energy efficiency, and resource efficiency. Also, I forgot to mention, but if you have any questions at any point, just feel free to interrupt me and we can discuss that. So are there any questions so far? If not, I will move on to the first topic for today. So let's see how can we rethink the design of serverless and microservice environments for performance. To this end, I will present 𝜇Manycore, a cloud-native CPU for tail at scale. This paper was published at last year ISCA. In this paper, we first did a characterization of microservice and serverless environments on conventional processors. And based on our insights, we proposed 𝜇Manycore. This is a processor architecture that is highly optimized for microservice environments. 𝜇Manycore was able to reduce the tail latency over the server class processors by 10 times and improve the throughput by over 15 times. So when we want to design a processor for microservices, we first need to understand why the current processors are not good enough for such environments. First, current processors are designed to maximize the average performance. You can think about caches, burn predictors, and many other structures that are designed to optimize for the average performance. However, they fail to meet the stringent tail latency constraints that are very important in microservices. Second, current processors are becoming beefier and beefier. They have larger caches, they have larger ROBs, load store queues, they have more complicated branch predictors or prefetchers. However, microservices, which again share the same properties as serverless environments, they have many requests coming in parallel. Those are bursts that we talked about. However, each request has very low instruction level parallelism. In current processors, we have monolithic cache coherence, which means that we have all the cores in our system, and as we go towards more cores, this becomes even more important. And all these cores are coherent with each other. All of these caches are maintained coherent among each other. However, in microservices, and even more in serverless, the requests of different microservices do not share writable data. They do not communicate with over shared memory. Instead, they use remote procedure calls. And finally, current processors are designed and optimized for long-running predictable applications, and therefore we have very complicated prefetchers, branch predictors, and so on. On the other hand, in microservices, we have short-running services. Each request is about tens to hundreds of microseconds, and this is a very dynamic environment with many bursts, with many context switches, and so on and so forth. So how can we use these insights of microservice environments to redesign the current processors? To that end, we proposed 𝜇Manycore. The basic unit of a 𝜇Manycore is a hardware cache coherent village. Within a village, we have a few very simple cores, so they do not need to be beefy cores such as Intel Sapphire Rapids, for example, cores. These cores are kept cache coherent. However, cores that are outside the village, which are in the same chip, are not coherent with each other. Each core has its own private L1 cache, and all cores shared L2 cache. Due to smaller instruction and data footprints of microservices, we do not need larger and deeper cache hierarchies. In addition, within every village, we have local and remote NIC and DMA engines. So local are used to communicate with villages within the chiplet, within the same chip, while the remote NICs and remote DMAs are used to communicate with outside our server. Finally, within a 𝜇Manycore, we have a hardware request queue that is enhanced to enable hardware request scheduling and hardware-supported context switch. So let's see what is this hardware for request scheduling. When a request arrives at the local NIC, the NIC will deposit those ready requests in the request queue. The request queue is a hardware structure that has for every request its status, which can be running or waiting, and the ID of the service. On the other hand, every core in our village will spin on a work flag, and it will execute dequeue and complete instructions. So what does it mean? It means that while cores is spinning on the work flag, once it detects that there is a request in the queue that it has status waiting, it will start running that request. That request will then switch its status to be running, and it will execute on the core. Once the request is completed, we will change its status to be finished, and the core becomes idle again. The idle core will keep spinning on the work flag, while the finished request will go again to the NIC to send the response back to the user. In this way, we do not have software involved in the request scheduling. Instead, everything is done by the hardware. Hardware request queue, hardware instructions such as dequeue and complete, and cores are spinning on their work flag. However, we said that during the execution, the requests themselves can get blocked, either due to going to the remote storage or going or calling other functions asynchronously. So instead of just having ready and running requests, these requests can be in blocked state. So what does it mean? How do we change our system to support such environments? We add additional status, which is in this case blocked, and we also add support to avoid operating system invocations and software overheads and do the saving and restoring of the request context purely in hardware. So in this example here, once the request gets blocked, core will first save the request the state of this request in the request context memory. The state includes all the registers, such as general purpose registers or some special purpose registers. This is a very small memory, which has about few tens of bytes per request. Once the request gets unblocked, meaning that we have received a response for this, either for the storage or for another service, we change again the status of the request to be waiting. This is done by the NIC, local NIC inside the village. The core will again become idle, and once it becomes idle, it will see that there is an old request that has its status to be waiting. In that case, the core will read the context from the request context memory and then start running the request. Again, once the request is completed, we'll mark it as finished and send to the NIC to the user. Our villages in 𝜇Manycore are grouped into clusters. We have multiple villages. In our implementation, there are 4 villages that have the same implementation with few cores, L1 caches, L2 caches, remote and local NICs, and support for request, hardware request scheduling and hardware context switching. Such villages are combined together with a memory pool, which stores a shared read-mostly memory, and a network hub into a cluster. Inside the memory pool, we use shared read-only data, such as large data sets or even container images for serverless environments, while network hub is used to connect together these villages with each other and also to connect them from the outside of the package or outside of our server. To connect many cores in our system, we use leaf-spine on-package network. Leaf-spine topology is used in data centers today in software environments. However, we observe that such system can be very efficient in our hardware schemes. Leaf-spine on-package network has many redundant low hop count paths between any 2 clusters. And you can see here in this diagram here how it is implemented. So every cluster will have its own network hub, as I described in the previous slide, and all network hubs are called leaves in our topology. On top of that, we have a few network hubs that are only network hubs. They do not have any other villages that are spines in our network topology. Every leaf in our cluster is connected to all spines in the topology. To make the system scalable, we also enable our topology to be hierarchical. It means that we organize a few clusters into one large pod and then connect it to first-level network hubs and then connect first-level network hubs to second-level network hubs. In this way, we can have many sources and destinations communicating with each other without being blocked. This is very important in microservice and serverless environments, as we have a lot of communication between services. We have lots of on-package networks, and therefore we need to optimize for both latency. So we need to have low hop count compared to, for example, 2D mesh, but we also need to have very high bandwidth because we can have many messages going from the same source to the same destination. So that's why we have all of these redundant connections between clusters. To evaluate 𝜇Manycore, we simulate a 1,000-core 𝜇Manycore. We use Dead Star Bench microservices, and we use Spin tool to extract traces running on top of SST simulator for cycle accurate timings. We also compare the power and area measurements using MACPAT and Cacti. We compared 𝜇Manycore to 2 baselines. First, we have a server class baseline that has 40 cores. Those are beefy cores modeled after Intel Ice Lake. And this server has the same power as 𝜇Manycore. A large manycore, on the other hand, has again 1,000 cores as 𝜇Manycore, but it does not have these optimizations such as 𝜇Manycore. Those are request scheduling and context switching, the optimized topology, and so on. These cores are modeled after ARM A15, so those are very simple cores. And this design has the same area as 𝜇Manycore. So in this plot here, I show the normalized tail latency of Dead Star Bench microservices, and everything is normalized to server class design. You can see that first, when we go from the server class design to large manycore, we already reduce the tail latency by quite a bit. The reason is that we don't need for microservices very large and beefy cores. Instead, we would prefer this scale-out design. However, when we go step forward and have 𝜇Manycore design, we significantly outperform both server class and large manycore designs. In fact, when we have high load, the tail latency in the 𝜇Manycore is reduced by 16.7 times over server class baseline. This is on average across all services, and 7.4 times over large manycore. So before I move on to the next topic, which is how can we rethink design to go only for not only for performance, but also for energy efficiency, are there any questions in the audience? Does anyone have any questions?
Okay,
Yes,
so
I have a question.
Oh, go ahead. I think we have a bunch. Go ahead.
Okay, sorry. Thanks. So great talk, Jovan. Sorry, I can't turn on my video apparently, but yeah. So I'm wondering about the performance slide. I guess slide 53, where you show basically when you compare this large manycore to the server class. So doesn't single thread performance still matter though? Like, how are you able to get such lower latency with much simpler cores? What else is happening here that contributes to this? Because I would still expect that, you know, the single thread performance is worse and this also matters. So I'm just trying to understand the results.
Yes, that's correct. So when you compare the average latency of server class and large manycore has much worse average latency. But because it has lower issue width, it has lower frequency, it has smaller caches, and everything that contributes to the single thread performance. However, when we talk about tail latency, the tail latency will be mostly affected by these queuing effects, by the contention. So if you have fewer cores, even though every single core is much faster, you will have much higher queuing delays. Also, these services will most of the time be idle, so they're not only executing, they don't run, they're not even sensitive that much to frequency, which I will show later. But because of this idle time within every single invocation, even though the single thread performance is lower, the idle time will dominate the total execution time. So by improving single thread performance, you improve this running time, but the wait time will still be more or less the same. So that's why scaling it out in this environment contributes a lot to tail latency. Average latency is worse.
Okay. What is tail here? Like 99 or?
Yes, P99, yes, correct.
Thanks.
Hey, Jovan, this is Boris Grad. Cool stuff. Yeah, unfortunately, I also can't seem to start my video, so I guess that's been disabled. So I have a question that is maybe a little bit philosophical, right? Because you're basically proposing, you know, what I would say fairly extreme specialization, right? Like entire CPUs, fabric and everything, right, for serverless. And, you know, serverless, you know, it's a decent fraction of the cloud market, but like, you know, does it make sense to specialize for just serverless? What are your thoughts on this? Like specializing scale, right? Like building CPUs and fabrics and everything.
Yes, correct. So that is true. This will be 𝜇Manycore is effective for serverless and microservices, and everything is basically IO bound. It has small footprints, and that suffers from context switching and request queuing. So it is only a fraction of the workload in the cloud. What we did in the latest work, which is Mosaic, I will present it in the end, is how can we introduce the minimal changes in server class processors so that we can run efficiently both serverless and non-serverless workloads. In this case, yes, we will get significantly improved both throughput and latency, but we optimize only for one class of workload. We're trying to make the server not to be accelerator-like, but still to be the general purpose CPU. So as we see workloads going more towards these fine-grained services or network applications, in that case, it would make sense. So to answer the question, yes, this is specialized. This is only for microservices/serverless workloads. These workloads are growing, so it would make sense in some future for cloud providers or for data center operators to go for such designs. But if we want to go for less intrusive designs, we can go for something like Mosaic that I will present a bit later. Yeah.
Okay. I mean, I guess like just to follow up, like I just want to, you know, say that if you think about, I mean, one of the really nice things about the serverless model from the provider's perspective, right? Provider's perspective is that with traditional VM deployments, which tend to be a bit on the beefier side than serverless, right? I mean, generally speaking, more memory, more CPU, they kind of end up with some stranded resources, right? Like literally a little bit of memory, right? Like maybe some CPU, maybe even like a fraction of a CPU slice. And that's where like serverless is just pure genius, right? Because they can just plug those gaps. And when you have multiple data centers, you have a lot of these teeny little holes. And it costs them very little in terms of software infrastructure, but they can actually monetize these little resource, kind of stranded resources that are otherwise very difficult to monetize. And I think that's a really useful perspective to have in mind, right? Because I think we as architects, right, and I'm also obviously an architect, and we've also proposed specialized hardware for serverless, is, we can just take this hammer and be like, hey, let's just throw a new chip at the problem, right? But I think it's good to think about the provider's perspective and try to understand why they would want something like serverless, and like how much extra hardware would they actually be willing to pay for.
Right. Yes. So again, we even have this analysis of what will be cost for cloud providers in the other paper. I can share that later. But yes, we also this won't be only for serverless in 𝜇Manycore specifically. So all of this work published by Google and Meta, that they say that their whole infrastructure is based on microservices, even though it's not a cloud environment, it's more like private data centers. Those would also benefit from 𝜇Manycore-like systems. So at least hardware support for request scheduling, for context switching, I believe that those would be very beneficial for them as well. So I think it would be serverless, yes, but also it would go a bit beyond serverless, such as these service-like environments from Google, Meta, Alibaba. They all have a bunch of papers describing their infrastructure as microservice heavy.
Cool. My very last point, apologies, and then I'll totally turn it back over to you, is we've actually proposed something very similar philosophically, kind of islands of simple cores with a fast interconnect and a shared cache for exactly these kinds of workloads. A decade ago, our ISCA 2013 paper called Scale-Out Processors. I encourage you to take a look.
Yes. I know for that paper. Yes. Yes. Scale-out NUMA, right?
Scale-out processors, no.
Okay. Yes.
I have a comment as well. So when we talk about big cores versus small cores, we should also look at the workloads, right? So the ones that you have mostly evaluated, these are all compiled ones, right? It's C++ and Golang, I think. That's right?
Mm-hmm. Yes.
So I think,
all these are C++ in this slide specifically.
Yeah, right. So just poking like a little hole in it. For serverless, it's mostly Node.js and Python. And in my experience, it does matter to have a more powerful core for this type, because just they are more verbose ones in terms of instructions. So maybe I would say that there is still some, I don't know, a little bit of research left there, because it would be actually very curious to see how good or bad it is for Python and Node.js, which is dominant in serverless.
So we did for the later slides that I will discuss, but we did also a study of popular functions in Azure, which are Python functions, and we observed that they have similar properties, which is lots of idle time, very small data footprints, very small instruction footprints. And we compared them, for example, to Cloud Suite applications, monolithic cloud applications, right, that are common benchmarks. And we saw that there is significant gap between the sizes of monolithic applications and these, even though those are in Python and as a non-compiled language, right? We have numbers. I don't remember them right now, but in the paper there are also like some numbers from these production functions, subset of production functions, of course. What are the typical sizes there?
No, this part I totally agree. But in terms of CPI, is there a difference in depending on whether it's compiled or interpreted, for example?
Yes, of course. But even for Python functions, I will show those later. They're not, for example, they're not sensitive as much to CPU frequency just because of these idle times, right? Because of their mostly network bound. Oh, if you talk about some other like ML inference, or if you want to put something else like matrix multiplications or something that is very compute heavy in serverless function, then yes, of course, it will benefit from larger, beefier cores.
Sure.
So I would say it makes it. I believe it's more about what is the functionality rather than what is the language. Yeah. But of course, there are overheads of non-compiled languages that are non-negligible.
Thanks. Makes a lot of sense.
Hi, I'm Shyam. I have a small question. So when you mention the tail latencies here, and all the services which are part of this microservice application are deployed on the same core, right? Like the same CPU. Like, okay, we have your 1,000 cores, but the same, all the functions are deployed on the same CPU chip.
Yes, yes.
Okay. So what do you think will be the impact if, let's say, the functions in the application are on different chips, and how would this compare to like a
Yeah, absolutely. Yes. So the environment here is that we have 8 services and 32 clusters within a chip. So we have cluster of number of servers. I don't have it top of my head, but it's either 8 or 10. And then we distribute those. So you have instances of each service both on the same server and on other servers. And when 2 services communicate with each other, they randomly take one of the instances that we have. So it's either within the same server or outside the server. So from these communications outside the server, we also have the network topology will help here. Network topology plus these remote NICs that we have will help reduce the network latencies there. So this is not like, these are not only on one server. We kind of emulate environment with multiple servers and inter-service communication as well, if that was your question.
Okay, yeah, that makes sense. I was just curious because how representative is this case where a lot of functions of one microservice application are all on the same chip? So I just wanted to ask.
Yeah. We simulate the environment with them being scaled out to multiple servers. Yes.
Okay, cool. Thank you.
Okay. Let me now continue towards the second topic for the day. So now that we have some base that we can optimize for performance, what about energy efficiency? So for energy efficiency, we have a paper which is EcoFaaS from this year ISCA, which is how we rethink the design of serverless environments for energy efficiency. We perform the characterization of energy efficiency in serverless environments, and based on our insights, we proposed EcoFaaS. EcoFaaS is a service-level objective or SLO-driven energy-efficient serverless system. EcoFaaS is able to reduce the energy consumption by 42%, while also reducing the tail latency by 35%. EcoFaaS is fully in software and it doesn't need any special hardware support. So this is run on regular server class processors. So how can we save energy in serverless environments? An obvious approach is that we can use very well-known technique, which is voltage and frequency scaling, or DVFS. However, what are the challenges if we want to use DVFS to get an energy-efficient serverless environment? First, serverless functions are highly diverse. We take many open source serverless functions and we run them at different frequencies of our core. In this figure here, I show the normalized response time when we change the frequency of web server application and video processing application. We can see that video processing is much more compute bound and therefore it is more sensitive to the CPU frequency. Therefore, as we operate in higher frequencies, it will have much lower response time. On the other hand, web server is IO bound application and therefore it will reduce only marginally its performance, even when going from 3 gigahertz to only 1.2 gigahertz. Second, serverless functions are composed into applications as compositions of multiple independent functions. So end-to-end application has multiple different functions. Each of these functions, if we want to think about their energy efficiency, each function has very different energy performance profiles. If the user wants to describe what is its optimal energy execution, it needs to take into account all of these profiles and the end-to-end application SLO. This creates a big mess. So we need to think about all of these profiles and the end-to-end application SLO. Instead, we believe that in energy-efficient serverless environments, users should only specify the end-to-end SLOs, while these breaking down the energy-efficient execution plan needs to be done transparently from the provider side. Second, as I discussed before, the idle time dominates the function execution. Either due to going to the remote storage or calling other functions, serverless functions spend majority of their execution time being blocked and waiting on I/O. Therefore, if we have many functions executing in the request queue and we schedule them for the execution, if we follow the current state-of-the-art systems that execute based on the run to completion model, it means that we will run this function and wait until it's completed before moving on to the next function. This means that we will also spend our idle time waiting on CPU cycles and spending the CPU cycles on non-useful work. Then, when the next request from the queue starts executing the core, because it was waiting for the previous request to be completed, it needs to run now at higher frequency. In this way, we spend a large amount of energy for no reason. Thus, in energy-efficient serverless environments, we should exploit the abundant idle time within function invocations. Finally, as we discussed before, we have very often context switches of different functions on our shared cores. However, these functions could have very different optimal frequency points to execute in the core. But changing the frequency of our cores are very expensive. If we need to change the frequency at every point when we need to switch between different functions that need different core frequencies, we need to go to the operating system, invoke the driver, and then go for these multi-millisecond overheads, which are very large for short-running serverless functions. This means that we, in serverless environments, if we want to achieve energy-efficient environment, we need to minimize the number of frequency changes. Finally, serverless workloads are highly dynamic. This means that if we want to keep some cores at a given frequency and then keep them all the time in those frequencies so that we can schedule requests that need a given frequencies to those cores, it will work fine at some point. However, very soon, we will have very different distribution of the workload. We will have more requests that need higher frequency, less requests that need lower frequency, and those requests that need higher frequency will need to run even higher because of the contention in the queue. On the other hand, cores that are assigned to lower frequency will be idle and waste our resources. In energy-efficient environment, we need to dynamically adjust our system to the fluctuating serverless workloads. So overall, we observe that conventional systems are not optimized for energy efficiency. They run constantly at the highest frequency because they consider all serverless functions as opaque boxes and do not know their sensitivity to frequency changes. And even if we want to use state-of-the-art power management schemes, they do not execute efficiently in serverless environments because they execute with run to completion model. On the other hand, serverless functions spend majority of their time being idle and waiting on I/O. Finally, if we have a single request queue that is shared across all cores in the system, we will need to tune the frequency of our cores on every context switch. However, as I said before, changing the frequency is very expensive in serverless environments. To address all these issues, we propose EcoFaaS, an energy management framework specifically designed for serverless environments. EcoFaaS has 4 key ideas. First, it is driven by SLO metrics, which means that the workflow controller in EcoFaaS will take the end-to-end application, which is in this case composed of 3 functions, and it will use its end-to-end application SLO. Then, before executing the application, it will offline profile these functions. It means that it will execute the function at different core frequencies and record what is its execution time and what is its energy. Then, it will take the application SLO and use the mixed integer linear programming to minimize the total energy of all functions within an application such that we make sure that the total execution time is lower than the SLO. When we use this MILP approach, we'll get the individual deadlines for all of these functions. So going from the end-to-end application and its SLO, we use the pre-profiled data from the functions to assign individual deadlines for all functions. Second, in EcoFaaS, we profile and predict the execution time and energy of every individual function invocation. So when a function executes, it will have its execution time, it will have running time on the core, and also idle time when it goes to the storage or call RPC other functions. In EcoFaaS, when a request for a given function arrives at the container along with its SLO, it will first be enqueued inside the handler's queue. Then a dispatcher process within the container will use the historic data to predict what is the execution time, what is the idle time, and what will be the energy of this specific invocation, taking into account the inputs for this invocation when running at different core frequencies. It will also use the predicted queuing time at all these different frequency pools and then decide where to schedule a request for execution. So it will schedule the request for execution in a core pool that minimizes the total energy consumption while making sure that the SLO for this specific invocation will be met. Third, EcoFaaS minimizes the number of core frequency changes by splitting the cores into frequency classes. So in EcoFaaS, we have core pools, which means that we have multiple cores running at the same frequency, and then a pool schedule, they schedule invocations that need that given frequency. So how we schedule requests with EcoFaaS? When we enqueue from the container of a function inside the frequency, inside the core pool, there is a frequency pool scheduler that maintains this queue. We schedule invocations that are ready for run on our available cores, and when once of these invocations gets blocked, the frequency pool scheduler will immediately schedule another ready-to-run invocation on that core. As all of these invocations are already registered with this core pool, it means that they all need the same frequency, the same core frequency. Therefore, we do not need to change any, we do not need any frequency changes on our cores. Finally, EcoFaaS changes pools and pool frequencies dynamically in order to maintain the fluctuations of our serverless workloads. So node controller in EcoFaaS will keep track of what its current system state and current system needs, and based on that, it will change the organization of cores into core pools. Specifically, node control will reconfigure the pools based on current system state. Every core pool will periodically report its utilization to the node controller, and then the node controller will decide how many cores are needed for each pool and what is the frequency of these cores. So if at a given point we will not need more cores at the highest frequency or the lowest frequency, those cores will be given to another core pool. In this way, we can meet the changes in demand of serverless workloads. To evaluate EcoFaaS, we use a cluster with 5 Intel Xeon servers. Each has 20 cores. We use both OpenWhisk and Knative infrastructure, but in these slides, I will present the OpenWhisk results. And we evaluate Baseline, which is state-of-the-art serverless platform at that time, which was our work from last year, ISCA. And on top of Baseline, we add Power Controller. This is a Gemini work published at Micro 2020. We compare everything, of course, to the EcoFaaS proposal. Here, in this plot, I show the normalized energy on y-axis for the baseline plus power control, and EcoFaaS. We can see that EcoFaaS can significantly reduce the energy consumption over both baseline and baseline plus power control. The main reason for that are, again, using the idle time of function to schedule other ready-to-run invocations and setting the core frequencies in a way that we do not need to frequently change them based on the workload demands. In fact, EcoFaaS reduces the energy consumption over state-of-the-art baseline by 42%. Before going towards the latest part of the talk, are there any questions for the EcoFaaS work?
Yeah, I have a question for you. Hi.
Hello.
Yeah, my question is, how significant is the power of a serverless function with respect to a virtual machine boot? I understand that you did not consider a VM here. So,
So this is all containerized environment. Everything is in OpenWhisk with Docker containers, and everything includes the cold starts. So we also have set of optimizations specifically for cold starts. So how to pre-warm containers, when to execute the boot up time on lower frequencies, and then even further reduce the energy and so on and so forth. So here is function. When I say function, it means the execution itself, but also the preparation of the container if we have cold start. So EcoFaaS optimizes for both sides, the energy of both sides, both the execution and the preparation.
Thanks.
I also have a quick question.
Mm-hmm.
I'm wondering about the assumption that there's an SLO with each request. So this is not really the current case in today's fast platform. So I'm wondering how you envision this would work in a platform. Like, I guess, you know, our users want their request done as soon as possible, but maybe the billing is affected based on what SLO they require. Or, you know, how do you actually envision the SLO part of this kind of platform?
Yes, correct. So that was the first part of the paper, was basically motivating for the need for SLO serverless, just so that we can use this Slack so that we can reduce the energy. In the evaluation here, we used SLO to be 5 times the execution time of unloaded system. So just we execute a function, then the SLO will be 5 times that. We envision this to be as some form of annotations, so that when you deploy the function, you can annotate it to be like what is the expected SLO in the terms of P99 latency that you meet that many requests as for the other cloud applications. But then the issue will be how to connect the SLO for different inputs, because every invocation itself will have different baseline execution time based on different inputs. So what we could do is to say that the accepted SLO would be something like n times the expected execution time on an unloaded system for these inputs. And then as EcoFaaS predicts the execution time on unloaded system, it will also say the SLO will be 5 times that predicted time. So that is how we envision it currently. And we believe that there is need to make very explicit interfaces how to define the SLO, either through the SLO can be, in this case, SLO is performance SLO, but SLO can also be the energy if some companies care only about the green environments and stuff like that. So SLO related.
The SLO is really the end user, the cloud user that says this, or it could be as soon as the request is submitted, the SLO is always 5 times unloaded type thing. Like there's kind of more from an infrastructure perspective.
So I believe in the long run, it should be very diverse, and then the users themselves should be able to specify it. But for now, for simplicity reasons, we use this 5 times. So it's much easier. It's more clean. But yeah, I think that, for example, if you go for serverless function that is doing web serve, you would need much stricter SLO than, for example, if you do parsing some documents or something like that, something that is batch workload. So in one case, you could use 2 times. The other case, you could use 10 times the execution time. So I believe that in the future, it should be user guided. But for now, for simplicity, we use just this 5 times.
Okay, thank you.
Yes. So I will, to conclude this talk, I will go briefly over the latest work that I did, which is how to improve the resource efficiency of serverless systems. To that end, I will briefly describe the Mosaic, which is the work accepted at Micro 24. And this is harnessing the microarchitectural resources of servers in serverless environments. In this work, we perform the microarchitectural characterization of serverless systems using both open source workloads and production workloads from Microsoft Azure. And based on the insights, we proposed Mosaic. Mosaic is a hardware-software co-design for microarchitecture resource efficiency in serverless environments. Mosaic can improve the throughput of serverless systems by 225% while reducing the power by 22%. The problem that we try to address here is that serverless environments inefficiently use microarchitectural stateful processor structures. When I say stateful processor structures, I mainly refer to caches, TLBs, and branch predictors, those structures that keep the state of our invocations. In fact, because of the frequent context switches, we interleave the execution of different functions of the same core, and therefore we pollute such structures. In this figure here, we show the normalized execution time on y-axis for different serverless workloads when we interleave the execution of 2, 4, 8, 16 functions, and when we clear the full structures on every context switch. So you can see here that the execution time can increase even about more than 3 times when we have interleaving of 8 or even 16 functions, which is a very common case in production workloads such as in Microsoft Azure. However, we observe there is an opportunity in small-size serverless functions. Serverless functions are known to have small data, instruction, and branch footprints. And in this figure here, I show the LC occupancy in megabytes for traditional monolithic cloud applications such as Spark, Hadoop, MongoDB, and so on, and for serverless functions. You can see here that the LC occupancy of serverless functions is very low. So we can use this small size to reduce the size of these large hardware structures, so we do not need the full size structures such as L2 caches, LC, TLBs, branch predictors, and so on and so forth. So instead of using these large structures, can we use fraction of these structures and preserve the state of serverless structures, of serverless functions within the fraction of the structures? In this figure here, I show the normalized execution time as we execute traditional monolithic applications and serverless functions with different sizes of LC. You can see here that while monolithic applications are very sensitive to the LC size, serverless functions do not change their performance at all when we reduce the size of LC. So we can use this insight to reduce the size of structures and use only fractions of structures to save the state of serverless functions. However, the main challenge here is that there is significant heterogeneity across functions. So in this figure here, we show as we change the L2 size in megabytes, what is the execution time for 3 different functions: RNN serving, image processing, and word count. So you can see here that while RNN serve is very sensitive to the L2 size, word count, for example, does not change its performance almost at all as we change the L2 size. And again, these are experiments done in a real platform. This is on Intel Sapphire Rapids that has support for both L2 and LC partitioning. So we want to use smaller sizes for serverless functions and save the state of functions in these fractions of size of structures so that we can use these on a context switch. However, different functions will need different size in these structures. To address these challenges, we propose Mosaic, a hardware-software co-design specific for serverless environments. Mosaic CPU is a processor architecture that can efficiently run both monolithic applications and serverless functions. So this goes again back to the discussion that we had earlier, that we want to have some CPU that can efficiently run traditional applications while it is optimized for serverless functions. So how can we introduce minimal changes to processor architecture so that we can run different classes of workloads efficiently? On top of Mosaic CPU, we developed Mosaic Scheduler, which is a software stack for serverless systems that maximize the benefits of Mosaic CPU. Mosaic has 4 main principles. First is that we partition stateful structures into per function tiles. So we have, for example, L2 cache in this figure that is partitioned into multiple chunks, and these chunks, composition of chunks, create a tile. Every function has its own tile, and tiles of active functions are put at high state, while functions of not active tiles of non-active functions are at low power mode so that we can save power and energy. In this way, we can save the state of different functions concurrently in different tiles. For example, function X and function Y can have their state in different tiles, so when we context switch between them, different functions can use their own tiles without getting polluted by previously running functions. Second, we will size these per function tiles in L2 cache, L2 TLB, LC, branch target buffer, and branch predicting table. So all of these 5 stateful structures in the core, we will size them based on the individual function needs. So some functions will get larger tiles, some functions will get smaller tiles based on their individual needs. Third, we will use performance modeling to predict the optimal tile size without going for the extensive brute force search for the optimal sizes. In fact, we will use the characteristics of functions such as its IPC, memory footprint, the number of instructions, the number of branches, and based on the already profiled functions, we'll predict the optimal size of our function based on the only high-level characteristics of the new function. So for this, we use a random forest predictor, and it has very high accuracy with very low overheads. Finally, we will tightly couple hardware and software to maximize the benefits. In fact, the hardware will expose its state to the software, so the software can offline predict the optimal size for the functions, and online schedule the functions on cores that are highly likely to have the state of that function. In this way, we can maximize the benefits of Mosaic CPU. We evaluate Mosaic and compare it to the state-of-the-art baseline, which is server-class processor based on Intel Sapphire Rapids. And we show here in this figure throughput in kilo requests per second for multiple different serverless functions. Again, these results are simulated using QEMU plus SSD. We can see here that Mosaic significantly improves throughput across all functions just because it is able to save the state of functions across context switches. In fact, Mosaic improves the throughput over server-class baseline by 225%. Mosaic, compared to manycore designs, not 𝜇Manycore, but just a large manycore that we discussed earlier, it has lower throughput by about 13%. However, it does not affect the performance of monolithic applications, while large manycore, because of its lower single-thread performance, significantly decrease the performance of monolithic applications. So to conclude, serverless computing is very beneficial. However, its current execution is performance, energy, and resource inefficient. In this talk here, I discussed about 𝜇Manycore, EcoFaaS, and Mosaic as a step towards cloud-native processor architectures. In addition to this, I worked on MXFaaS, SpecFaaS, and SmartOclock, which are software systems for microservices and serverless environments, and also on rethinking the virtual memory system for cloud-native applications. To conclude, there are lots of opportunities to rethink the hardware-software abstractions for the emerging cloud workloads such as serverless and microservices. I hope that we can together work on these topics and move serverless environments even further and get them in a place that we can get both benefits that we have today, but also to have high performance, low energy consumption, very efficient resource consumption. With that, if you have any questions, I will be happy to take those questions now.
Hi, I have a question about the last work.
Yes.
So in the first figure you show the functions, for interleaved executions. Yeah, this one.
Mm-hmm.
Each function, like as you said, each function is so small, and my question is, how can they pollute the macro architecture state so much so they can have this much like a slowdown?
To answer your question, first, as you can see, depending on the size of the function, for example, for video processing, as it's larger function, when we interleave in the executions, the response time will be degraded less. However, for shorter functions such as image processing or social network, the pollution will have a higher impact. The reason for pollution here is conflicts. Plus, as you can see here, the jump when we go from 2 to 4 to 8, 16. So as we have more and more functions that are different functions, we will have more pollution. So large number of functions that interleave plus conflicts in caches, TLBs, and branch predictors. And keep in mind that in fully secure cloud environment, the actual execution will be clear all, which means that whenever you have context switch between different functions, you flush all the structures. Otherwise, you can have side channel attacks. So even if serverless function is small, conflicts are there, plus many of them execute on the same core, and that's why they pollute the structures.
Okay, I see. Thank you.
Yes, yes.
Hi, Jovan. So when you're designing hardware, like sending different like so-called requests to the computing cores in the first paper, the 𝜇Manycore. So do you do any like core or cross-core load balancing, or you just spread them randomly or in some certain order, or do some round robin?
Yes, so there we have multiple instances of service that is inside different villages. Across villages, we have a round robin load balancing, and then within a village, 8 cores share the same queue. So those cores will load balance basically by fetching data from that queue. So a random round robin across instances, and then within instance, 8 cores. Whenever core becomes idle, it fetches the request from the queue locally.
Okay, got it.
Yes. I think we're over time, right?
Yeah, I also have a question about your last paper.
Yes.
So you said in normal, like in secure situations, you flush the caches to minimize the sidechain effects, right? Then in your implementation, in my understanding, because most of these serverless functions are rather small and they don't share a lot of memory pages, so they get flushed often and they don't use that much, not large caches. So you split the caches into chunks and let functions use that portion of cache as a kind of like a scratch pad. No. But like you try to let the functions keep their caches, right? So
Yes.
will this cause any sort of side channels also?
So of course, you will need these fractional caches to sometimes assign to different functions. So on a context switch between functions, if you reassign chunks to different functions, you would need to flush those as well. If you don't reassign chunks across functions, those are just different functions using different fractions of caches, they cannot see anything that the other function is doing. So you cannot see any replacement of data, you cannot see any prime and probe attacks, all of these are not enabled. So we improve security in this way, but if you want, again, fully secure, whenever you reassign chunks across functions, then you need to flush those. But when you flush a chunk, which is about 1/16 of a full cache, it's much faster than flushing the full cache.
Also, is this chunk size can be reassigned on the fly, or you have to spend some milliseconds or some time to reinitiate this configuration?
So it's not milliseconds, it is few microseconds reassigning time, because you need chunks of different functions are not visible to cache coherence protocol, and that's why you would need to still flush those dirty lines there. So you don't need to flush the read-only lines, but you need to flush the dirty lines because they will not be visible to cache coherence protocol anymore. So that will introduce a few microseconds on a context switch. Yeah. And that happens only when you change the owner of the chunk. So only when you reassign chunk across functions, which is not the frequent case.
Okay, thank you.
So is this cache partitioning variable size or fixed size?
So cache is partitioned into chunks that are fixed size, and then function is assigned a number of chunks, which can be from 1 to 16. So size of the function is variable, but chunk is fixed.
So the granularity is the chunk. Okay.
Correct. Yes. And chunk is it's basically set-based partitioning. So chunk is a few sets and all ways of those sets.
I see. So this decision is made by your Mosaic scheduler, which is
Correct.
intermediate between the cloud scheduler and Linux scheduler.
Yes, yes, that's correct. Yes.
Okay, thanks.
I think
Yeah, that was a great discussion. Many thanks to Jovan and the audience. It was very interactive. I think it was also very dense at the same time. It's great. Thank you, Jovan, so much. We'll be happy to publish it on YouTube. I think that will create a lot of interest online as well. Yeah.
Yeah, thank you very much for inviting me and for all the great questions. I really enjoyed it.
Yeah, that's great. Thank you so much. Thank you, everyone. Have a great time of the day or night.
Thank you.
Thanks.